Hi, I'm Kiranmai. Welcome to my channel Chemistry Tutorials by Kiranmai. In last video, we discussed about the phenomenon like diffraction and interference, which was explained by the wave nature of electromagnetic radiation. In today's class, we are discussing about particle nature of electromagnetic radiation. Particle nature of electromagnetic radiation explains the nature of emission of radiation from black bodies, ejection of electrons from metal surface when radiation strikes it, variation of heat capacity of solids as a function of temperature, line spectrum of atoms with special reference to hydrogen. These observations can be explained only when we consider the particle nature of electromagnetic radiation. In today's video, I am discussing the nature of emission of radiation from black bodies, that is black body radiation. The nature of emission of radiation from black bodies. When we observe hot objects, there will be an emission of electromagnetic radiation. That is, when we heat an object, it will release electromagnetic radiations of different wavelengths. That is, hot objects emit electromagnetic radiations of different wavelengths. Hot objects emit electromagnetic radiations of different wavelengths. Say some radiations will be at the wavelength of 450 nanometers, 700 nanometers, or 1000 nanometers. 450 nanometers, 700 nanometers, 1000 nanometers, or 800 nanometers, like that. It's different wavelengths. Corresponding to different wavelengths, electromagnetic radiations are emitted by the hot objects, particularly at high temperature. At high temperature, an appreciable portion of radiation will be in visible region of spectrum. So in electromagnetic spectrum, which is divided into the regions based on their wavelength, it is divided into radio waves, microwaves, ultraviolet rays, visible rays, infrared rays, x-rays, and then gamma rays. In these electromagnetic spectrum, at high temperature, when hot objects get heated up, when it acquires high temperature, it starts releasing electromagnetic radiations which will be in visible region. So at high temperature, an appreciable portion of radiation will be in the visible region of the spectrum. When the radiations emitted are in visible region of spectrum, we can see the objects glowing. That is, we can see when the bulb gets heated up at particular temperature, we can observe the filament glowing. So at high temperature, the emitted electromagnetic radiations will be in the visible region. Further, as temperature increases, higher portion of shorter wavelength is generated. Let me explain this one with an example. When you see in furnace, when we heat iron rod is heated at particular temperature, you can observe the tip of the iron rod which we are heating will be in dull red. if we further increase its temperature, we can see the color changes from dull red to more red color, that is bright red. If we further increase the temperature, this red color goes on changing to white, and then we can observe blue color. From blue color, see, when iron rod is heated in the furnace, first it will be in dull red. On further increase in temperature, on further heating, we get more bright red color, and then when we continuously increase its temperature, the tip of the iron rod which we are heating turns blue color, that is the color will be changed. See, in VGR, this radiation, when we see RB, wavelength of red light is longer than the wavelength of blue light. Wavelength of red light will be around 750 nanometers, and wavelength of blue light will be at 400 nanometers wavelength. See, as temperature increases, a higher portion of shorter wavelength is generated. Here the shorter wavelength is blue. So at initially the iron rod turns red color, which have high wavelength of about 750 nanometers, and we are increasing its temperature. Then it starts emitting electromagnetic radiations which are in blue color, which corresponds to shorter wavelength 400 nanometers. So as temperature increases, the emitted electromagnetic radiations with the shorter wavelength will be in higher portion. This means that intensities of radiations of different wavelengths emitted by hot body depend upon its temperature. That is, if the temperature is lower, it emits the radiations with particular range. As we increase the temperature, at the difference in temperature leads to difference in the wavelength emitted, difference in the electromagnetic radiations wavelength. So intensity of radiation of different wavelengths emitted by hot body depend upon its temperature. So in general, hot bodies emit electromagnetic radiations of different wavelength, but at particular temperature, electromagnetic radiations of particular wavelength get prominent. So at particular temperature, red length, red waves, that is electromagnetic radiations corresponding to red light will be more, that is it will be more when compared to other electromagnetic radiations. At particular temperature, blue light is more prominent, that is other electromagnetic radiations will be there, along with it blue light is emitted but in more quantity, that is more intensity. See, this means that intensity of radiations of different wavelengths emitted by hot body depend upon its temperature. So it is temperature dependent. At particular temperature, particular wavelengths are more prominent. Further, when objects made of different materials, say like a copper, iron, like that, if we take different types of solids and keep at different temperatures. See, you are taking iron piece and copper piece and keeping at a particular temperature. Then these two solids, irrespective of the material by which it is made, emits the same amount of radiations at the same temperature. Objects made of different materials, when kept at different temperature, emit different amount of radiation. Irrespective of the material we are taking, if we place an iron rod at particular temperature and observe the radiations emitted, and if we take copper and we kept at the same temperature at which iron rod is placed and observe the electromagnetic radiations emitted, we can find the same electromagnetic radiations wavelength. That is, there will not be a change in emitted electromagnetic radiations dependent on the nature of material. It only depends upon the temperature at which the material is placed. Hope you understood this point. And also, when the surface of object is irradiated with electromagnetic radiation, part of it is radiated or reflected. Part of it is reflected. When the surface of the object is irradiated with electromagnetic radiation, these electromagnetic radiations which we are irradiating are not totally absorbed by the object. Part of it is reflected. That is why we are able to see the colors. That means white light falling on the leaf. If you consider the white light falling on the leaf, the surface of the leaf absorbs all the light except the radiations which correspond to the color green. This green light is reflected back, so only we can observe the green color. See, when the surface of the object is irradiated with electromagnetic radiations, these electromagnetic radiations have different wavelengths, and in these electromagnetic radiations, few radiations with particular wavelength gets absorbed and some of the electromagnetic radiations will be reflected. This is because all objects are not perfect absorbers of radiation. That is, in general, objects are imperfect absorbers of radiation. It will not absorb all the radiations of electromagnetic radiations. Part of it will be reflected. This is because objects are imperfect absorbers of radiation. So, then which objects absorb complete radiations means in nature we cannot find any ideal body which absorbs all the radiations. If an ideal body absorbs all the radiations uniformly and it emits all the electromagnetic radiations observed by it, then that body is known as black body, and the radiations emitted by such body is known as black body radiation. An ideal body which emits and absorbs radiations of all frequencies uniformly is called a black body. Means it absorbs all frequencies of radiation. It absorbs radiations of all frequencies, and after absorbing these radiations it will emit it. It absorbs radiations and also whatever the electromagnetic radiations absorbed by it will be emitted back. Then that ideal body is referred to as black body, and the radiation emitted by such body is called black body radiations. Means whatever you supply the energy, all these energy will be absorbed, all these electromagnetic radiations will be absorbed by it and it will be emitted back. So, a black body will be in equilibrium with its surroundings, thermal equilibrium with its surroundings. It absorbs the energy and it gives out the energy. So, the net change in thermal energy will be zero. A black body is in thermal equilibrium with its surroundings. So, it is a perfect radiator of radiant energy and it will be in thermal equilibrium with its surroundings. So, a black body absorbs the electromagnetic radiation and it emits electromagnetic radiation. The amount of light or electromagnetic radiation emitted, that is intensity of electromagnetic radiation from a black body, and its spectral distribution, that is the emitted electromagnetic radiation's spectral distribution, depends on its temperature. So the amount of light emitted by the black body and so the intensity and its spectral distribution, that is these emitted electromagnetic radiations wavelength corresponds to a particular region in the electromagnetic spectrum, that may be invisible region or ultraviolet region or infrared region. This spectral distribution depends only on its temperature. See, at lower temperature the black body emits radiation in the longer wavelength. As the temperature increases, the emitted electromagnetic radiations shift to shorter wavelength, that is the spectral distribution depends only on its temperature. Intensity spectral distribution depends only on its temperature. Means the black body emits radiations depending upon its temperature. At a given temperature, if we draw a graph between intensity and wavelength, let's take at T1 temperature. Okay, at a given temperature, first intensity of radiation emitted increases with increase in wavelength, increases with increase in wavelength, and then reaches maximum value. Then it decreases with increase in wavelength. So at given temperature, intensity increases with increase in wavelength, reach maximum value, and then decreases with increase in wavelength, decreases its intensity with increase in wavelength. So here see, at T1 decrease at a given temperature, let's say at T1, intensity will be increased with the increase in wavelength, reaches maximum point, and then intensity will be decreased but the wavelength will be in increasing order. Next, if we compare two temperatures, if we compare two temperatures, let's take another temperature which is higher than T1. Let it be at T2. The temperature first initially increases, reaches maximum point, and then decreases with increase in wavelength. See, as the temperature increases, intensity increases, reaches maximum value, and then decreases with increase in wavelength. This is at T2. T2 is greater than T1. So, as the temperature increases from T1 to T2, lambda max value, this is lambda max, maximum amplitude, maximum lambda max value, that is amplitude of, that is highest intensity point, lambda max, maximum of curve shifts towards, maximum intensity of the curve shifts towards shorter wavelength. Maxima of curve, lambda max, maxima of curve shifts towards shorter wavelength, means the peak shifts towards the shorter wavelength. So as temperature increases, maxima of curve shifts to right, shorter wavelength, shorter wavelength. As we discussed earlier, red color which has maximum value of 750 nanometers at particular temperature, and at particular temperature blue light is emitted with increase in temperature, blue light is emitted which have 400 nanometers. See, means it is shifting to shorter wavelength. According to classical physics, if we go on increasing the temperature, then the intensity of electromagnetic radiation should also be increasing, but in practice, but in reality, it is not like that. As we go on increasing the temperature, the intensity will reach the higher point and then it gets decreased. This cannot be explained by considering wave nature of electromagnetic radiation. Max Planck in the year 1918 he also won a Nobel Prize for considering electromagnetic radiation with particle nature. That is, earlier electromagnetic radiations are considered to be wave-like, means electromagnetic radiations have only wave nature, like that they considered. But to explain these black body radiations, wave nature of electromagnetic radiations is not sufficient. Then Max Planck came with his theory, Planck's quantum theory, through which this black body radiations can be explained. Let's know about Planck's quantum theory. This Planck's quantum theory, proposed by Max Planck, brought a huge revolution in physics and led to the foundations of quantum physics. He also won Nobel Prize for this theory in 1918. So according to this theory, Planck's quantum theory, atoms and molecules, atoms or molecules, atom or molecules could emit or absorb energy only in discrete quantities of energy and not in continuous manner. See, if this atom emits electromagnetic radiation, this will be in small packets of energy which is discontinued or separate discrete quantities, but not in continuous manner. When we discussed earlier, atoms or molecules or the objects release electromagnetic radiation in a continuous wave like nature. But according to Planck's quantum theory, it is not a continuous energy one, but it emits or absorbs radiation in the form of discrete quantities, that is, separate quantities of energy. Next, this small amount of energy. See, this small amount of energy that can be emitted or absorbed in the form of electromagnetic radiation is known as quantum. Known as quantum. So, the electromagnetic radiations will be in the form of discrete quantities of energy, and the smallest quantity of energy that can be absorbed by atoms or molecules or emitted by atoms or molecules is known as quantum. See, this quantization, this quantum can be compared with the staircase or ladder. See, in ladder you can step on these steps, one step on any step at a time. See, a person can stand on a ladder either on one step or the other step, but he cannot stand in between these steps, right? Similarly, in electromagnetic radiation, atom can absorb energy, that is, it can absorb this quantum or two quantums or three quantums, but not here. It will be in energy gap, right? It cannot absorb continuously, but it can absorb in packets of energy. So this one is quantum. And then he also explained the relation between energy and frequency of radiation. He said that energy of radiation emitted or absorbed is directly proportional to energy of radiation emitted or absorbed is directly proportional to frequency of the radiation. So, energy of the radiation emitted or absorbed is proportional to frequency of the radiation. If the radiation frequency is high, the energy absorbed by the emitted or energy absorbed or emitted will be high. So E is proportional to mu, and E is equal to h mu. Here h is Planck's constant. And it has the value of 6.626 into 10 power minus 34 joules second. So, Max Planck's quantum theory considers electromagnetic radiations as particles but not waves, and these particles of electromagnetic radiations are called photons, and the smallest amount of energy is called quantum. So this is Planck's quantum theory. Based on this Planck's quantum theory, Einstein successfully explained photoelectric effect. This will be discussed in the next video, photoelectric effect and all. So in this class we discussed about the nature of radiation from black bodies and also Planck's quantum theory. If you understood this content, like this video and share with your friends. Thank you.